Hi, today we're looking at the fundamental theorem of calculus, a very important theorem for us. Now, before we go into the fundamental theorem, let's kind of do a lead into it by looking at the velocity curve. Now, when we talked about Riemann sums, we learned that the area under a velocity graph is going to give us meters. And we can do that by making these little tiny rectangles, right? Where the width is going to be in seconds, the height is meters per second, and we get meters. So we get distance, or more importantly, a change in distance. And we're going to talk more about that in just a few moments. Now, we also know area, we get area by taking the antiderivative. If I take the antiderivative of velocity, dt, from A to B, this is going to give me my area. Well, since we just found out that area is my change in distance, right? This is going to give me my change in distance then. Now, we have a fancy word for that, displacement. When we covered particle motion, we also talked about something else about displacement. We learned a more formal rule for displacement. It's going to be the change in position, right? Now, in other words, it's going to be S of B minus S of A. Remember where S is a change in position right here. And remember, S of t is the antiderivative of velocity. This right here is what we call the FTC. It's very easy to use. So let's take a look at an example. Well, first of all, let's write out what the FTC really says. It says if we take the antiderivative of a derivative from A to B, what we get is the difference in the values of the function, not the derivative. Remember, the function is position here. The derivative was velocity. So we're going to get the change in the function, f of b minus f of a. Not the change in the derivative, but the change in the function. And that's really what FTC says. Area, in a nutshell, area is the difference in the values of the function, not the derivative. So let's take a look at an example on how we can use this. Let's say we're going to take the antiderivative from 2 to x dx. Now, this is an easy one. We can graph this one. If I graph it, it goes from 0 to 1, has a height of 2. I can find the area pretty easy. 1/2, the base is 1, the height is 2, and I get 1. But let's see if our integral works as well. Now, what the rule says to do, to get the area or to solve the antiderivative, I have to find the function. And that's easy. Take the antiderivative, we get x squared. We evaluate it from A to B by subtracting their differences. So I write a little bit differently. 0 to 1, no more an integral, and this is going to become f of 1 minus f of 0. And I can just plug those in. What is f of 1? Well, that's just 1 squared minus 0 squared. And look, we do get 1. Just the same. Now, for a triangle, it might be easier to draw. But some graphs aren't so nice. So let's take a look at some slightly more challenging ones here. Ready? Let's take a look at number 2. What if we had something like x squared minus 3 dx from 3 to 4? And I want to evaluate this integral. I want to find the area underneath this curve. Well, if I try drawing it, well, it is a parabola. Starts at negative 3, goes up here. I want to integrate from 3 to 4. Well, this time, it's not so pretty. It's not a rectangle. Now, I could use Riemann sums, but I want to get accurate. So I take the antiderivative, because the antiderivative, remember, it finds us area. Minus 3x, and we're going to integrate this from 3 to 4. Now, how I write this? Now we're going to evaluate f of 4 minus f of 3. And I just plug them in. Plug the 4 into both. This becomes 64 over 3 minus 12, and I plug into 3. 27 over 3 is 9 minus 9. Oh, how nice. That just becomes 0. So what I'm left with is just a 64 thirds minus 12. And you can leave it like this, or you can simplify it. Whatever that becomes, that's 36. I like to simplify necessarily because sometimes it takes a lot longer. 6, that becomes 8, 28 thirds. Okay, and I might even be wrong on that. Just leave it like that. So let's take a look at another slightly challenging one. Let's go from -2 to -1 of the following. X minus 1 over x squared dx. Well, I am going to rewrite this, okay, and we get -2 to -1, x minus x to the -2 dx. When I integrate this now, from -2 to -1, I get x squared over 2. Be careful, minus, it becomes x to the -1 over -1. Notice no plus c, by the way. We don't put a plus c because these are what we call definite integrals, okay? These are definite integrals because we know what the answer is going to be. We're going to get a definite answer. And I'm going to rewrite this one more time. -2 to -1, I get x squared over 2 plus 1 over x. Ugh, yucky. And now I apply the FTC, which says f of -1 minus f of 2. You will like this because you don't necessarily have to simplify. If I plug -1 in, I get 1/2. Be careful, minus 1. Plug in the 2, I get 2 plus 1/2. Oh, this one works out nicely. You can leave it like this, or you can simplify it if you want to. We're just going to get -3 because the 1/2s will cancel out. Let's take a look at a trig one, number 4 here. So if I take a look at a trig one, let's try the antiderivative from 0, let's say to pi over 4 of the secant squared of x dx. Well, I know this antiderivative. The antiderivative of secant squared is just tangent of x. And if I evaluate it, f of pi over, pi over 4 minus f of 0, I'm looking at the tangent of pi over 4 minus the tangent of 0. Well, tangent of pi over 4 is 1 minus 0. I get 1. We're number 1. So that's basically what we're going to be doing on these, okay? So take a look and practice some, get a few more there for you. All right, see you later. Bye-bye.